Hello, everyone. We are Team 24084, and we are part of the Chemical and Environmental Engineering Department here at the University of Arizona. Our project is titled Dialy-ssist. We will be breaking down our project as seen on our poster. First, we will talk about the introduction, and then we'll move on to materials, results, environmental impacts, economics, and finally, we'll close out with next steps. So starting off, our project, once again titled Dialy-ssist, is aimed at creating a filter to be paired with any dialysis machine currently on the market. This filter will filter water from the spent dialysate that is created when going through dialysis treatments. The problem that our project is trying to solve is the fact that dialysis takes relatively an enormous amount of water. During one treatment, the dialysis machine will go through 40 to 80 gallons of water. And over the course of a week, this could add up to 80 to 160 gallons, depending on the treatment duration and the amount of days in a week a person undergoes dialysis. This water may not be available everywhere. For example, in water-scarce areas, this amount of water may be hard to come by or be really expensive. And it is important during dialysis to have a clean source of water during natural disasters. Our project is aimed at being able to recycle water initially used in dialysis during these times. For example, our aim is to have somebody undergoing dialysis hook up to a sink, like is done during normal dialysis. They turn on the water, and then once our storage bags are filled up with an appropriate amount of water to complete a full dialysis treatment, the water from the sink is shut off, and the spent dialysis, and therefore the recycled water, is continuously recycled throughout the entire treatment. Our hope is to cut down the amount of water to about 6 gallons. As for the materials we used for our project, all of it was theoretical. We used MATLAB in order to model the absorption and therefore determine the purity of each of our filters, and optimize for the mass of absorbent needed in order to reach our final purity. Visio was used to create all of our PFDs and BFDs, as will be seen later on. We used GREET to determine the amount of water used to create each of the filters. Finally, the absorbents that we used are as follows. We used a virgin coconut shell charcoal to remove urea, creatinine, and uric acid. This activated carbon is not in powdered form. As with powder, we wouldn't be able to maintain a high enough pressure in order for water to continuously run throughout the system. Next, we used urease. We used a jack bean powder urease to remove any excess urea that the activated carbon did not remove. Next, we used two different zirconiums. First is zirconium hydroxide in order to remove the phosphate. And then finally, the zirconium phosphate, also in a powder, to remove the ammonia created during the reaction of urease and urea. Finally, we have our two water polishers. We have a cationic DI resin and an anionic DI resin. Both of these are from amberlite. The cationic DI resin is an amberlite IR252. This removes all the cations, like calcium, potassium, sodium, and magnesium. Finally is our anionic resin, which is the amberlite IRA420, and this removes all of our anions, such as chlorine.
Next, we'll be looking at the results. Spent dialysate contains various toxins. Our system, based on extensive modeling, has the potential to remove nearly 100% of these targeted contaminants. While existing research supports the absorption capabilities of our chosen materials, Further experimentation will be necessary to confirm actual removal percentages and any kinetic factors influencing the process. Here's a breakdown of our system's operation. Our feed stream is the effluent of the next stage dialysis machine or any dialysis machine. The effluent is first pumped through a UV light filter, eliminating all present bacteria. Next, the stream enters a reactor vessel containing activated carbon and urease suspended in activated carbon. This is where urea, creatinine, and uric acid are treated. Next, the stream is sent to the zirconium canister, where the ammonium and phosphate are removed. And finally, it passes through the DI resin canister, which treats ionic molecules created from the UV light filter. The now purified water can be directed towards two destinations: storage bags for later use, or back into the dialysis machine for immediate reuse.
Next, we'll be speaking about the environmental section. The environmental impact per 3-hour treatment of dialysis was assessed, and it was determined that the water used without the dialysis system totals to about 25.2 liters of water per treatment. Using the GREET life cycle analysis software, it was determined that 1.01 liters of water would be used to manufacture this system. And then, using the energy components of the UV filter and the pump, it was determined that the dialysis system would use about 0.234 kilowatt hours per the 3-hour treatment.
Next, we'll be looking at the economics for the project with equipment cost and energy consumption. The product of each filter was based on optimization through theory, with consideration of materials being bought in bulk for experimentational purposes. It is assumed that each filter would be replaced on a weekly basis and that we would be using 3-hour treatment cycles for power consumption reasons. Next, we'll be looking at the next steps for our project moving forward. First, we would like to try to merge the activated carbon, the urease, and the zirconium filters into one filter, reducing the overall number of filters. Second, we would like to perform experiments to determine optimal mass of absorbance, experimental purity, optimal canister sizing, and inaccurate water requirements. Third, we would like to determine the shelf life of each filter for storage purposes if it was to be used in a hospital.
In conclusion, we have theoretically created a 3-filter system in order to recycle water from spent dialysis. In the future, we wish to do more experimentation just to solidify that our system actually works with actual spent dialysate.
That concludes our presentation on dialysis. Thank you for listening.